far. One of them says, "I think I just lost an electron." To which the other one says, "Are you sure?" The first one replies, "I'm positive." Hey Olivia, don't you ever think it's weird that we're just on this device that we have no idea how it works?
Not really.
I don't think you really understand the gravity of the situation.
Why are we friends?
I'm sensing a little friction. Anyway, maybe we should really figure out how these things work before we go down.
Ooh, what's this? Roller coaster G-forces. Roller coaster rides are notorious for creating accelerations and G-forces? This is too complex. We need to go home and figure this out.
Olivia and Alana, I had so much fun with you guys at the roller coaster this weekend, but I was wondering, how do they work? I was afraid I would fall right out of the car when it went upside down. Would you explain it to me, you geniuses?
Ugh, this is so hard. I'm not getting anywhere with these equations. They don't make sense. I have to call Alana and see if she's getting this.
Hey, what's up? Oh no, yeah, I'm working super hard on it. Okay. Alright, I'll be right over. Grandma wanted to know how the loop-the-loop works since she saw us ride the Desert Storm. So let's start with centripetal force first. The main forces that we have to factor in are the forces of gravity,
Which pushes objects towards the ground.
and normal force, which is the force the ground pushes up against the force of gravity.
Don't forget centripetal force, which is the force moving towards the center of the circular motion, and this can be applied to Desert Storm.
So basically, when entering the loop-the-loop, there is acceleration into the loop to ensure that the car will get all the way around.
And Grandma probably won't know what acceleration is, so we should tell her that it is a change in the velocity, and she probably won't understand velocity either, so we can just say it's the speed that goes in one direction.
Perfect. So we will start the car just sitting at the bottom of the loop, hypothetically.
So the forces are acting on the car at this time are the gravitational and normal forces. The gravitational force is pushing the car into the railings, and the normal force is the railings pushing into the car to support it, and so it won't end up on the ground.
Okay, then as the car is accelerating, we have the car sitting at the top of the loop, but upside down. How crazy is that?
This is where it gets a little tricky. So both the normal and gravitational forces are pushing down towards the ground. The normal force is pushing down because the ground is always pushing up towards the object.
So since the car is upside down, it helps to think the ground is also upside down. That is why the two forces are pushing in the same direction.
And the reason why the car can make it all the way around the loop is because of the acceleration and the centripetal force. The centripetal force always pulls towards the center of the circle, so with the right amount of force and the centripetal motion, the car will be able to make its way all the way around.
Plot twist! You also need to take into account the clothoid shape that is applied for roller coasters. This shape is like a teardrop, and they are applied to roller coasters because with a bigger radius at the bottom, this reduces the amount of force on the car when it's going super fast on the bottom. This is also to prevent the acceleration from snapping people's necks in midair.
So now for some calculations to put our knowledge to the test. Let's create a hypothetical situation. How about we are on the ride, so the mass would be 115 kilograms? That sounds about right. Then the radius is 7 meters, and we don't know the velocity. So let's figure it out.
Since the minimum velocity can always be found when Fn equals 0, we have to plug in the 0 for Fn in the equation, and the problem will end up having the gravitational force equal to the centripetal force.
Then write out the variables for what each force represents. So the masses cancel, and then we are left with the square root of g, which is equal to 9.8, and multiply that times r.
Yay! We're so close to figuring out the minimum velocity. So that ends up being 8.2851, but we'll just round. So the minimum velocity is 8.28 meters per second.
I'm so excited we finally figured it out. It was really throwing me for a loop.
Me too. Let's go on one last ride.
Oh, Alana and Olivia, thank you so much for explaining that to me. I don't think I'll go on the next ride, though. I'm not lazy, I'm just overflowing with potential energy.